the stability means that we have G equals R or GC, and the change of G is less than the change of the R. If this inequality holds, then this crack, after the propagation, the crack will stop. You still remember, right? Okay, then we talk about the D control and the loader D control and loader control. Here, this is the crack size. You can see and how for the displacement control and for the loader control, and how the G and R they are changing with respect to crack size. Based on this figure, so you can see for load control, we can see that for the load control, and this is the change of this load control, the G is positive, right? You can see it's positive. However, this is for displacement control, it becomes smaller and smaller. So this is the so here is at this point, guys, you can see at this point, when the G equals the R, at this point is going this way. So this is instability. So for the load control and for this displacement control, we have these kind of these figures. And then here is an example, and I'm going to show you the example. And for this is a DCB. What is a DCB, guys? And DCB is a double cantilever beam, right? So suppose we have a crack and we just pull it using the same displacement. Here's a crack, and here's a load P, and here's a load P, and this is called D, C, and B, and double cantilever beam. And this is a double cantilever beam. And for this case, and we know that, and you can look at the lecture 5, guys. And lecture 5. For the lecture 5, so cantilever beam, you have lecture 5, right? So this lecture 5, and at the very beginning of lecture 5, and we have the G. This is we have the G for load control, guys. For load control, the G equals P squared and A squared and B E I. So this is how we get for this double cantilever beam, and how we get the G. The G is related to the crack length, and the thickness of this is the beam, Young's modulus, every moment of inertia, and P is a load. It's a constant load. And based on this one, guys, right? Based on this one, so this is for G load, and then we take a look at the DT and DA. As I told you guys, how can I check whether this is a propagation is unstable or stable? I just check DT DA, okay? And DT DA for P, and DT DA for P here. And so this is the P, and the DT DA, and for P load, this is A, and we can easily get that. So DT DA equals 2, and P squared A, and BEI. So BEI. So this is, and we can just write this equals 2G and divided by A, and which is greater than 0. But because energy release rate is always positive, crack length is always positive, and we can from here we can get so the change of this G is always positive. Right? And however, for the displacement control, that's another story. And for D-controlled, we need to use the equation at the very beginning. And we need to use equation and use this equation. G equals the P and 2B and dP and dA and use this one, right? We need to use this equation and to get. So this is dG dA. So this equation, for this equation, we know for the D control, okay? So from the beam theory, and so we know that T can be written as 3 and delta EI and 2A and power 3. So you can just take the derivative. You can see on dP dA, then dP dA. So keep in mind this is part of denominator A power 3. And so you can just plug in and you will have we will have this equation. So this is the dG and dA. So this is equals minus 9 delta square EI and B A power 5. So this one and can also be written as this is the minus 4T and divided by A. So here is the minus sign here. We know that this guy is always less than 0. So this is the G, okay? So this is dG dA. So this is the G, and this G is for the displacement control. We have this one. We just plug in. We have this one will give us the 9 and delta square EI 4B and A power 4. So this is G. And then after we get the G here, and then we just take the derivative again. And then we'll have this, because G is always positive, A is always positive. This is a minus sign. And we have this always less than 0. That's the reason we have this is a D controlled, the TR curve is always goes this way. You understand? You understand, guys? Okay, for flat R curve, the crack growth in a load control is always unstable, while displacement control is always stable. If the ZR, if it is for flat R curve, and flat R curve and goes this way. So this is the TR. So here is AA and flat R curve. So here is A0. Right? As I said, because for the load control, and so as long as you go through this point, and then this is load control, so this one is keep growing. They keep growing. And however, for this is the D control, it always goes this way. It always goes this way. If it goes this way, at this point, if the G equals R, okay, it will grow a little bit and then stop. Why? Because this G is going down. G is decreasing. G is decreasing at this. If I have a new this A1, I say it's A1. At this A1, for this A1, this is R is greater than G, so the crack stops. You understand? Alexis, you understand to you? Okay. So that's the reason we have this comment. For a flat R curve, and crack growth in load control is always unstable because the G is changing, G is increasing with respect to A. However, for the D control, and it's always stable because for the D control, the G is going down, G is decreasing. Make sense? Okay. Then we look at this one, the structure with a finite compliance. So here is the two extremes. You can see most real structure are subject to the conditions between load control and pure displacement control. So this intermediate situation, can be schematically represented by a spring in series with a float the structure. Look at here. So this is CM and this is a cracked body. So this structure is fixed at a constant remote displacement, and this is a delta, okay, delta temperature, delta here, so delta T, and the spring represents the system compliance CM. So here is the CM. The CM is a compliance. For D control case, for D control, CM equals 0. For D control, CM equals 0. Equals 0 means that this guy is infinitely stiff machine. Why? Because if the crack changes, but the displacement does not change. Load is changing. No matter how you change the load, the displacement does not change. And we can say this guy is CM equals 0. CM equals 0 means that it's extremely stiff. Make sense? Okay. For load control, guys, because the load, okay? For load control, you can imagine load control means that my load does not change. And however, the crack is continuous. It's continuously growing. And continuously growing, that means displacement is growing. So load does not change, but displacement keeps growing. Then we have, this is called CM equals 0. So infinity soft machine is extremely soft. When the system compliance is finite, the point of the fracture instability obviously lies between the existence of pure load control and pure load control. And however, determining the precise point of instability obvious here, requires a rather complex analysis at the moment of instability. The following conditions are satisfied. And G equals R, okay? So G equals R, energy release rate equals resistance, and at this point, dGdA, the change of energy release rate with respect to the crack length, and is equal to the change of the resistance with respect to crack length. So dGdA equals dGdAP minus dGdPA minus this one. So this is the equation. So this is called this equation is called the Hutchinson and the Paris. In Paris, you guys know Paris, guys? Dr. Paris, Paul Paris, you know? He worked at SLU for 1 year in 2013 to 2014. He is a very famous guy. So this is Paris, this is the purpose. Okay, I want you guys to take a look. I don't want you guys to know how to get this equation, but to broaden your knowledge, you can just take a look at Appendix 2.2 and to have a better understanding of this equation. What? Bobby?
What are the delta t and the a subscripts in that equation?
Delta T is here, the displacement.
What does the t mean?
And T is a certain temperature.
Oh, okay.
Okay? Questions so far? So you don't need to worry about this one, okay? This because this is the long derivation and this long derivation. And then so here is so the lecture 5, and then we look at lecture 6. So for lecture 6, guys, we talk about the stress analysis of cracks. So for certain cracks, the configuration subject to the external force, it is possible to derive a closed form expression and for the stress in the body. Okay, this is possible. And for certain cracked configuration, however, most of the time we cannot get the closed form expression. Can somebody tell me what is a closed form expression? What is a closed form expression? Bobby?
For stress?
Whatever we see the closed form expression, what is the closed form expression? Equation, right? Closed form expression means equation. If we can derive, we can describe on some quantity by using an equation, and that means this guy is a function of something. So this is a relationship can be described using an equation or bunch of equations, and then we call this closed form. And then we call this is an analytical solution for something, not just for stress. Can be stress, strain, and other displacement and other things. Any questions so far? So this is a closed form, okay? So as I said, for certain cracked configuration, and we can get this, but most of the time, no. That's the reason we need to resort to the numerical simulation. For example, we use FEM and we use finite FVM, finite volume method. And maybe we use other things to describe this kind of relationship. Questions so far? But for this one, we just focus on a simple one. So here is several genus. Okay, so for in the body, assuming isotropic linear elastic material behavior. What is isotropic? Isotropic means that this material has the same mechanical property in all directions. Understand? For any generic point, for any isotropic means direction. For any generic point, so the mechanical property in all directions are identical. This is called isotropic. And another concept is homogeneous. Homogeneous means that for different locations, and they have the same mechanical properties. So homogeneous and isotropic. And for here, we also say isotropic, linear, elastic material behavior. So here are several the genii, the Westergaard, Irwin, Snedden, Williams, and they published such solutions. We'll look at it here. Okay, so this is crack, and so this is the equation and give the stress field in any linear elastic cracked body. So suppose this is a crack. So here is a crack. This is a crack tape, and we establish the XY coordinate system using this crack tape as origin. So this is X. So this is Y. For any given point, generic point in the neighborhood of this crack tape, and so this point is described using these polar coordinates, r the distance and theta orientation. And so this is sigma ij can be obtained using this equation. So this equation, what this equation says? So here is a k is so we can here, okay? And theta is a stress tensor. Theta ij is the stress tensor. This guy has 6 independent stress tensor. R and theta are defined in this figure. Okay, R and theta is a distance between the point of interest to the crack tip, and also this is the theta is orientation. And Fij is a dimensionless function of theta, and in the leading term, and Fij. R is a distance, and what is the k here? And we are going to talk about this one. So here is a summation, m equals infinity, and so here is a very, very long. And we usually take care of this leading term, because this leading term is dominant. But and look at here. For higher order terms, am is the amplitude and Tijm is a dimensionless function of theta for the mth term. And the high order terms depends on the geometry, but the solution for any given configuration contains a leading term for here that is proportional to 1 over square root r. So here, and you can see when r goes to 0 and sigma ij goes to infinity. This is understandable, right? Based on this equation, when the denominator approaches 0, what will happen to the value? Function value, the function is infinitely high. So this way, this sigma ij goes to infinity if r goes to 0. That means sigma ij is proportional to the 1 over square root r. So here is called singular. This case is a singularity case. Whenever you hear singularity, that means the denominator of something goes to 0. As a result, the function value is going to blow up. This is called singular. Right? When the denominator approaches 0, this function value is infinitely high. And if the denominator value equals 0, so this equation blows up. Questions so far? So how to derive this equation? I will not ask you to do that, but I'm going to show you very briefly, okay? So this is a lot of fun. Playing the derivation is very fun, very boring. Do you guys have the math manner? Who is the math manner? See, Casey, do a math manner, right? Yes. So I give this assignment to you. I'm derive this one from very beginning to very end. I'm kidding. For this one, okay, so I think most of you guys maybe have already know that. If you do not know, let me reiterate. And so for the generally speaking, for the crack, we have 3 different case scenarios. One is the crack opening, just as this one. And second one is the sliding. Along this is the crack face, the sliding. And third one is outer plane tearing. This way, outer plane tearing. So this is 3 case scenarios. So the first one is the most commonly seen one, and we are going to focus on the first one. So opening, mode 1, sliding, mode 2, and the third one is outer plane. This is shear or tearing. We call tearing. We can see this one, okay? So for mode 1, you can see sigma ij equals can be written using this equation, and for mode 2 with this equation, for mode 3 with this equation. And keep in mind, Fij1i, Fij2, and Fij3, they are totally different 3 functions. Alright? They are totally different. And we call Ki, K2, K1, K2, K3. And what are the K1, K2, K3 guys? Stress intensity factor. So you can see for these 3 guys, we can just describe these 3 guys using the stress intensity factor along with the square root of 2 pi a and a function, dimensionless function, to describe the stress distribution just in the neighborhood of crack tip. So you can see each mode of loading products produces that singularity 1 over square root of r, right? So as a crack tip, but the proportionality constants k and Fij depend on the mode. And the stress field ahead of the crack tip in isotropic linear elastic material can be found in that equation 2.37. These three equations, A, B, C. For mode 1, mode 2, mode 3, respectively, are in a mixed mode, while more than one load mode is present. The individual contributions to a given stress components are additive. Alright? They are additive. You know additive, right, guys?
Yeah.
Additive. Additive means that we can this kind of this principle of superposition, right? Based on this mode, you calculate a set of the solution. Based on that mode, you calculate another set of motion of the solution. Then, when these two gets applied together, and for the solution, you just add them together. This is called the principle of superposition, right? So the assumption is the material is linear elastic. So here sigma ij total equals sigma ij1 plus sigma ij2 plus sigma ij3. So this is principle of linear and superposition. You guys still remember this one? If you have taken CAE with me, and you will know, you know that. Questions so far? Guys, are you listening to me or you are doing something else? Huh?
Listening.
Okay, good. So here are the equations. Okay, here's the equations. As I said, there is no need to memorize, but you need to understand. And you can see table 2.1, mode 1, mode 2, sigma x, sigma y, and tau xy. And so you can see for here, we differentiate two case scenarios. One is a plane strain, one is a plane stress, right? And plane strain means that the plate is thick. Plane strain, I'm sorry. Plane strain means that the plate is thick. Plane stress means the plate is thin. And we focus on 2D, okay? We are focusing on 2D. So this is mode 1, mode 2. This is sigma x, sigma y, and tau xy, sigma z. For different case scenarios, we have different sigma zz. And keep in mind, for the plane stress, these two components are equal to 0. For plane I'm sorry, this is mode 1 and mode 2, guys. Okay, mode 1, these three equations hold for both plane stress and plane strain. For sigma zz and equals 0 for plane stress, and sigma zz equals this one for plane strain, and also for tau y xz and yz, they are equal to 0. And this is for both mode 1 and mode 2. Questions so far? So this is the stress field. So here is a displacement field. So keep in mind, they are different. And the displacement field. And also, on theta, okay, you know, theta and r. And for the displacement field, ux, uy, we have 2D. And we introduce a kappa here. And kappa is very similar to lowercase k, but we call it kappa. And what is the kappa? And kappa equals 3 minus 4 nu, the plane strain for plane strain. And kappa equals 3 minus nu divided by 1 point nu for plane stress. And for this is for mode 1, so this is for mode 2. We are not talking about the mode 3 because mode 3 is auto plane theorem. Okay? You understand? We are only focused on this is the plane. So that's the reason we only focus on mode 1, and mode 2. Questions so far? Bobby?
What happened to that large term in the stress field, like the AM R squared G? Where did that all go? Or like, how come that got rid of that in the
Sure,
stress?
I'm going to show you.
Okay.
Good. Okay. That's good. So we are taking care of the leading one only.
Okay.
What? Yeah, as the Bobby asked, where this one? Where this one? Here is the derivation. Okay. So Casey, finish this one for me. In the following week. Maybe Bobby can help you. Okay, here guys can see. And for mode 3, mode 3 is we have these values: tau xz, tau yz, along with the uz, and we have 3 equations. So here, so this one, the stress normal to the crack plane in mode 1. For the mode 1, only for the crack opening. So here is a r distance. Here is sigma yy, and how the sigma yy changes. So you can see over here. Here is the stress sigma yy, and this one is a sigma infinity. And we just assume theta equals 0. And theta equals 0 means that the orientation of this position is just along this crack surface horizontally. Okay? So this is the singularity dominated the zone. This is the singularity dominated the zone. So this is sigma infinity. So when you apply the sigma infinity.
Is that the like applied stress, like the global stress?
You apply it, right?
Okay,
When you this is sigma infinity is infinitely this you apply the load.
Okay.
Apply the load. Questions so far? No questions? And here is the derivation. Okay, so this derivation is very entertaining, very entertaining for math the students. We just go through very quickly, but if you are very curious, and you just take a look. I know a lot of students are feel very bored now. But you can see, okay, so this one we just use the sigma for the mode 1. Mode 1 is Ki sigma 2 pi r Fij theta, and this is higher order. So this is crack tape. So this is in front of it. So this is the perpendicular, and we have any point of interest, the r distance between the point of interest and the crack tape, and also the orientation theta. So derivation of the sigma field. Okay, so for the equilibrium, equation, have you guys ever learned the equilibrium equation? Equilibrium equation. If you have learned the sigma, if you have learned the say with me sigma ij, comma j plus fi equals 0. So this is the Einstein notation or initial notation. So this is based on the x, y, and z. So this is x, y, z coordinate system. And however, so this equilibrium equation actually it has 3, okay? It has 3 equations, but I just write this one using the Einstein notation, using one equation to accommodate all these 3 equations. Using one equation to accommodate 3 equations, and however, if we write this equation in the polar coordinate system, we have this. We have this. So we have sigma r, sigma theta, and this is tau r theta. So these 3 guys, So these three equations can be rewritten using these two equations. If these two equations hold, that means this point is in the state of equilibrium. If these two equations do not hold, any of them does not hold, that means out of equilibrium. Okay? So you can see it is from here. Let's go through very quickly. So you know this is every stress function, right, guys? Who have taken CE with me? Raise your hand. Computer-aided engineering. Michael, did you take the CE with me? No? Bobby?
No, I don't think it's offered anymore.
Yeah, I know they cut it off. They cut it off, but some students in 2002 took this course with me.
No, I didn't take it.
Okay, so it does not matter. Okay, so if this is the case, the area stress function, it is the phi is a area stress function phi. So area stress function says that the false derivative of phi stress function, which is equal to x1, plus the false derivative of phi, which is equal to second one, is a 2d and 2xy, and plus 2 d phi 4 dx1 squared dx2 squared. So this one equation holds. And then for here, okay, we have r and theta. We have two this is variables. And we just write sigma theta, the d phi dr squared, and drr equals this one. So this is r yr squared d squared phi squared d theta squared plus 1 over d phi dr. So we write these three equations. The equilibrium and compatibility equations are automatically satisfied if this is delta 4 equals 0. If this one equals 0, and then the equilibrium and the compatibility equations will be automatically satisfied. Okay, guys, because you have not taken the computer-aided engineering with me, so I will not bother to introduce one to you guys. But you can see. So here, equilibrium and the compatibility equations are automatically satisfied if this equation holds this equation. And so this one equals 0 is equivalent to this one equals 0 and boundary condition. You can see the boundary condition. And for theta equals positive pi, and for theta equals positive pi and negative pi, and for this corrective, guys, you can see for this position, just see the very sharp, okay, very sharp correct. So here is a positive pi, and here is a negative pi, right? And I know that, and for this is the correct, and we do not have any the stress values. That's the reason the boundary conditions for theta equals positive pi and negative pi, and we know that sigma theta and tau sigma and tau r theta equal to 0. So there is a Williams expansion. This is a Williams expansion. So I would suggest you take a look. I will not. And finally, guys, we will have this equation. I just read very everything in detail. And finally, we have this one, this LEF1, sigma r, sigma theta, and sigma tau r theta. And for model 1 and model 2, and you can see sigma is is proportional to R 1 over R squared. And epsilon is also 1 over proportional to 1 over square root of R, but U is R 1 over 2. So you can see, for these equations, you can see stress and strain, and they have singularity, but for displacement, no singularity. But for displacement, there is no singularity. Why for displacement there is no singularity, guys? Bobby? Why for displacement there is no singularity?
You can't have infinite displacement or.
No, you can see here, because the U is proportional to a square root of R. The R is a numerator, it's not in the part of the denominator. Right? But look at this sigma and the epsilon, both of these two guys, they are proportional to 1 over square root of R. When R goes to 0, and so these two guys blow out. That's the reason this is singularity. But for U, when is R equals 0, U equals 0. Right, guys? Questions? Comments? Remarks? So my bottom line is that if I give you a problem, you can use the equations we have to calculate the things. Alright? The derivation here, if you are very, very interested in, and I would suggest you go through and you will be entertained, especially the math minor KC. If you guys, other guys are interested in the derivation also, and you will be entertained. I read this very, very everything in detail. All this is the steps in detail.
Is the derivation in the book or is it just
The derivation is in the appendix, but here the derivation in the appendix is not as good as what I wrote. I'm sorry, I'm self-bragging. But this one, because I want to show my students, and I have more comments and make it more understandable. But for the equations in the textbook, they just give you all these things. They do not tell you on how they get these things, how they get that things. As I said, if you are interested in the derivation and spend 2 hours to look at this one, and you will have a better understanding of the equations. However, if you think that I just need to know how to use these equations to solve problems, I hate derivation. It's still okay. Okay? Then I'm going to give you the homework 2. If you have not turned in the homework 1, and you need to turn it now. Otherwise, I will give you homework 2. Okay, without further ado, I'm going to end today's session, and I hope you have a wonderful weekend.